All right, everyone. So welcome to a new Gattocast episode. It's been a while since the last time I produced some kind of original content on this channel, and this time I wanted to talk to you about something that struck a chord in me because the thing is that, as you might know, I haven't been working in cosmology and astrophysics for a while now that I switched to data science and machine learning, but. But still, I sometimes read the news, and I was very interested by this recent controversy that turned out that was covered by the media on the newspapers and some other media sources. So they were talking about this controversy, about these new findings about the age of the universe. So what is this whole thing about? So there's a new telescope called the James Webb Space Telescope that was launched 3 years ago by the NASA. And as with every new tool that is providing new observations of the universe or of any other physical phenomena, there's associated also, it's very common to find then some new discovery. And that's what the community, astrophysical community, was hoping with this telescope, and that's what happened, so as it seems, because it turned out in the very first years of these observations that there were some weird results, so some unexpected results, something that was not so easily explainable, that was not understood in the context of the theories that were known so far. And it again, due to this unexpectedness, then it was challenging basically these theories of structural formation and of formation of galaxies in the universe, and the formation of the universe as a whole. Now I'll talk more in detail about this later, but the whole idea that you get some observations of galaxies, very, very far away galaxies, and then these observations challenge the whole paradigm of cosmology, so the whole structure of how we interpret the data. So we have a dominating paradigm in cosmology, which is called the lambda CDM model, and it's basically the most successful model, mathematical model of the evolution of the birth and evolution of the universe. Now, this can explain a lot of phenomena. I'm not talking about this in detail because this is something I did a few years ago with the very first Gattocast episodes. But the idea is that you have a mathematical theory that explains what happens in the universe. So why do galaxies form that way? How many galaxies do we find at different points in time, and so on and so forth. So it's a mathematical theory of the universe, how it is born and how it evolves. So evolves means how do structures grow? How do we go from the Big Bang and the initial distribution of particles in the universe? How do these particles then sort of conspire to build up stars, and then the stars build up galaxies, and how do the stars and galaxies then join, so are grouped inside clusters of galaxies, and so on and so forth. So why is this interesting for me? Why did this struck? It really was really a sensitive topic for me, because what I read in the media was that the first observations of this James Webb telescope were regarding very massive, extremely large galaxies. So galaxies that were very heavy, very, very early on. And this means that since you're not supposed to find these objects, it means that it must be something that we don't understand in the theories of how these objects form. Let me explain. So we know that in the lambda CDM model, so the standard cosmological picture, we get we start from a distribution of gas, pretty fairly homogeneous. You have some fluctuations in the density of gas at the beginning of the universe, so very few moments after the Big Bang. You have the whole universe. You don't have stars, you don't have anything, you just have hydrogen and then some helium and some of the other elements, but it's mainly hydrogen. So these hydrogens then collapses, in the sense that if you have some overdensities of matter, these overdensities, they will exert some gravity, so they will sort of call to themselves the other particles, and so you will end up with growing these overdensities, and these overdensities eventually will grow into stars. The stars will merge, sort of will bind gravitationally and form the galaxies, and the galaxies will also on other larger scales will merge, and not merge, sorry, but they will be gravitationally bound within what we call clusters of galaxies, so large objects that are like, we can see, for example, stars as like single houses within a city, which is the galaxies, and then all the cities together, they form a nation, and that would be our cluster of galaxies. So just to make a very down-to-earth comparison. Now, what's the thing here is that if you look back in time, so like this James Webb telescope is doing, if you look at things that are very, very remote, very far away, what happens is that you're basically looking back in time. So the farther away you look, the longer the light that comes from that source takes to reach you, which means that it will be light that has been emitted many, many more years before. And so what happens then if you find something that is really large, really early? Since it takes time to build up massive structures, it takes time to form stars, it takes time for stars to coalesce and sort of bind within structures that are the galaxies. It takes time for galaxies to grow, because galaxies grow with a small size, and then they grow like eating sort of via merger. So they eat sort of their smaller neighbors, and so they grow in mass like the Milky Way did for many years, until it reaching the actual size. But like basically every galaxy has this kind of history. So what happens then, as I mentioned, what happens if you find something that is too large, is so large that you don't expect it, and it didn't basically have time to grow? What happens then is it's a problem for the structure formation theory. So it's a problem for the cosmological model that is describing how these structures form. It's a problem in the sense that you don't expect these large structures to form so early. You would expect small structures, and these small structure with time then they would grow that size. Now, this is an interesting topic then. There's many things that you can do, and we will talk about them a little bit later on, but the idea is that there might be, usually physicists and astrophysicists get very excited when there's some unexplained phenomenon, and they try to challenge the current theories and propose new theories, or simply come up with new theories or modification of the old theory to sort of account for this new phenomena. And why was this interesting for me, again, is because it was basically the first paper that I published. It was the subject of my first paper. So let me just now talk about this. My first paper was published in 2011 when I was doing my PhD in Madrid, and it was talking about variable dark energy in a form that is called vector dark energy. Again, it might be complicated to go into the details of all this, but the idea is that in lambda CDM model, in the standard dark energy, so in the standard universe, in the standard model of the universe, we have a form of dark energy which is called lambda. So this lambda is a constant dark energy. So it stays constant throughout the whole history of the universe. What we did in this first paper, we were studying, in my first published paper, we studied a source of variable dark energy, so which was not constant in time, and it was this variable dark energy was called vector dark energy. It was a model developed by some scientists at Universidad Complutense. I was in the Autónoma, by the way, but we collaborated on this paper. And why did we study this model? I mean, they were developing it on other grounds, but then we find out in those years there were observations of very massive galaxy cluster at pretty high redshift. So high redshift means back in time. Redshift is a measure of distortion of light that is basically the higher the redshift is, the higher the age of the source. So it's a way of measuring the age of an object in the universe, looking at how red the light is, how red shifted the light is, how much this light that is being emitted has been distorted. So it's a way of looking at the light and telling how old the source that emitted this light is. And what we did with this first study was to get this observation of very massive and old galaxy clusters, and see how well or not well they could be explained within the context of standard dark energy, which is lambda CDM, or other alternative theories like variable dark energy, which is what we did. Now, this is a reference. I remember this interview was my first scientific interview, and it was pretty weird for me because I didn't think anyone would find that interesting apart from me and my collaborators at the time. But anyway, so we were talking about this dark energy, vector dark energy model, which I don't think it's been studied anymore. It had some other issues, other phenomena it couldn't explain, but so it's been dropped as far as I know. But again, the interesting thing within this context is that it turned out it could explain this galaxy cluster. So this is interesting because as I mentioned, what happened with the claims with the James Webb Space Telescope is that these massive galaxies at high redshift, so old galaxies, are very massive and they are challenging the cosmology. And what we found 13 years ago with other observations, and it was a completely different thing. Now we're talking about galaxy clusters. I mean, it's not the same kind of observations. It's not completely different. The idea is actually the same. So we are looking at old objects that were very massive in another range. I mean, they were not single galaxies, they were galaxy clusters. So which means that we are looking at clusters as groups of galaxies. And we came up with this paper. So this is the actual paper. The first thing was just the press release that we got, the interview we got with the New Scientist paper. And this was the actual paper, which was called Vector Dark Energy and High Z. Z is the redshift, so high redshift massive clusters. And we're talking about a bunch of objects. There were like 3 massive clusters that were observed in some galaxy surveys in those years. And what you read here is that assuming Gaussian initial condition, which is sort of one of the tenets of the standard cosmology, the theoretical expectation of detecting such objects is lower than 1%, basically. So we discuss the probability of finding these objects in the light of vector dark energy. So the problem back then was that we had these very massive galaxies, and they were a problem for lambda CDM in the sense that we couldn't explain with that model, with that theories of gravity, how could such massive objects form in such a small amount of time. Which means there must be some kind of mechanism that we don't understand, that is not part of the standard model. It's either we change the laws of gravity at some point, either we change the laws of expansion of the universe. It's either how these galaxies assemble. There might be any kind of thing, any kind of approach that you can take in explain this phenomena. What we did was studying this vector dark energy model. So we were changing the nature of dark energy. So we are studying a different theoretical explanation of dark energy, which had a reflection, of course, also in the observation that you expect. Because once you have a theory, you can compute what this theory predicts, and then you compare it with the actual observation. And this is what we did. So back then, what we did was computing. Now you see this table here. We were now. I don't want to go too technical, but the idea is that we had these theories. We can do simulations of these theories. We can see how many massive galaxies we get, how many massive clusters of galaxies we get with time. So we can, if we run a very large simulation, we expect to have a larger number of objects, of course, because we got a larger volume, but then we look at the number density. So we want to look at the density of objects. So how many of these objects do I expect to find in a volume. And now we compared these objects. So we compared our simulation, with the volumes that were taken by the observations. In other words, we had these observations. We knew that these very large, massive clusters that were taken within these volumes were found. Again, we knew what was the volume of the survey. So when these surveys are done, when the experimental device is looking at space, you know what kind of volume is looking at and how many objects it has been finding in this volume. And so we have a density of objects. We can calculate it. And we do the same thing, but with simulation. So we simulate the theory. We implement our theory within a cosmological simulation code. This is what I did, was part of my of my PhD thesis. And then we computed the number density of objects. How many massive galaxies do we find? How many massive clusters of galaxies do we find in a volume that is like the volume of the survey, of the observational survey, and has the same mass, at least the same mass or larger than the object that we find. And we compute the probability of finding these objects. And we did this for different models. So what does this mean is that we simply got the different laws of physics implemented within the simulation code, and these different laws of physics will give different results in terms of what we expect to see in the universe. And if we did that, we computed the number of objects. What we see here is that this is like the number density, the probability of finding this kind of objects within this volume at higher redshift, so redshift higher than 1, in the different cosmologies. And this number is larger. If you look at this, just look at this number, is 0.007 in lambda CDM, but it's at least 3 times as large if you take a kind of vector dark energy models. So like these two. Now I want, again, I am not entering into the details, but just to wrap everything up, the idea here is, again, we did simulations of the standard model and non-standard models, and the non-standard models were providing much more massive galaxies than the non-standard, than the standard one, so than lambda CDM. And this is a typical thing, like you change the model, you find some observation that fit better, but then others don't. And in the end, again, we had to drop these vector dark energy models for other reasons, but in this back in 2011, it looked like a nice candidate, and it had this nice result that could explain better the presence of these objects. It could explain why these surveys were finding these very, very massive objects that were otherwise unexpected. And the interesting thing here is also that we could do this kind of studies with a very small number, because when you're looking at densities, even if you have one objects within a large volume, it's already telling you something about, of course you have error bars, but it's telling you something. It's telling you something about the nature of the model that you are studying, or the nature of the theories that you are studying. So this is the end of the first part of this podcast dedicated to the age of the universe controversy. I thought I might split into 2 parts. So the first part was dedicated mostly to my work on the subject many years ago, and the next part we'll meet to talk about what happened then nowadays with the recent James Webb Space Telescope observations.